Welcome back to this next video in which we are discussing linear combinations and span. Okay, so in the previous video what we did is we defined what a linear combination of a set of vectors is actually equal to, and we also saw what the span of a set of vectors is and how of course it's related very much so to the concept of a linear combination. Indeed, it's just the subset of the vector space containing all linear combinations of a set of vectors. Okay, what we now want to do in this next video is show that the span of a set of vectors, which at the moment we know is a subset of the vector space capital V, is actually a subspace of the vector space capital V. And let me just remind you of what is meant by a subspace of the vector space capital V. So a subspace is a subset of the vector space capital V, which, when you restrict the two composition laws of the vector space, addition and scalar multiplication, down so that they're just now relating to the elements of that subset. Okay, so when you restrict the composition laws down to the subset, the subset with those restricted composition laws of addition and scalar multiplication on it actually obeys the axioms of a vector space in its own right. So the concept of a subspace is a vector space within the larger vector space, basically. Okay, now what we do in the video on subspaces of vector spaces, which is earlier in this playlist on vector spaces, is we prove that in order for a subset to be a subspace, you actually only need to check 3 criteria. Okay, and that's wonderful because you'd think you would have to check all of the different axioms of the addition composition law and the scalar multiplication composition law, but you don't. There are 3 criteria that if those criteria are true, you can instantly conclude that the subset is in fact a subspace. Okay, and we go over why those criteria achieve that in the video on subspaces of vector spaces. Okay, so what we're going to do now is we're just going to prove that the span of the set capital S is always going to obey those 3 criteria no matter what the set of vectors capital S is equal to. Okay, so let's go over the page and make sure that these 3 criteria are indeed satisfied. Okay, so what was criterion number 1? So criterion number 1 first. So criterion number 1 concerned closure of the subset. Okay, so what it says is that you take any 2 vectors within the subset which you're checking whether it's a subspace. Okay, so W and W bar, let's say, which in this case need to be elements of the span of S. And I think I'll just draw a picture to make this a little bit more intuitive. So here we have our whole vector space, capital V. Okay, so I'll colour this in as always in turquoise. And then we've got our subset here, which is the span of S. Okay, so here is the span of S. Whoops. Right, so let's colour the span of S in orange here. Right, so we've now taken any 2 vectors that you like from this subset, the span of S. So W and W bar, they're just elements of this subset, span of S. So here's W and here's W bar. And what we now want to prove is that if you add them together, so W plus W bar, you must also end up with an element that's also in the span of S. So this is basically saying that when we restrict that addition composition law down to the subset capital W, or sorry, not capital W in this case, span of S, that it must be closed basically. Okay, so I'll draw a picture here of the composition law. So here is addition. Okay, and of course addition was defined on all elements of the entire vector space. So we had all elements of our entire vector space capital V here. Okay, and we had all elements of our entire vector space capital V here. Okay, so we could add together any 2 vectors from the vector space capital V. What we're now going to do is restrict it down just to the elements of the span of S. Okay, so let's say that the span of S elements are just this portion. Okay, so all the elements of the span of S, they are these rows of the addition composition table here. So this is span of S here, and I'll just colour that in. So all the elements of the span of S are these rows in our addition composition table here. So the rows down here in the addition composition table, these correspond to the elements outside of the span of S. And I would just like to circle span of S in orange. Okay, then all of the elements of the span of S have these columns up here. Okay, so these are the columns which relate to elements of the span of S. So we now just want to restrict our addition composition table down to adding an element in the span of S to another element in the span of S. So we are only interested in this portion of the addition composition table. I do not care about the other three quadrants here. I don't care about adding elements of the span of S to elements of the vector space outside of the span of S. I don't care about adding elements outside of the vector space outside of the span of S to elements in the span of S. That's just the same as this quadrant here. And I certainly don't care about adding together two elements that are outside of the span of S. So I only care about this portion. And basically what I'm now demanding is that if I add two elements of the span of S together, okay, and get an answer within this restricted addition composition table here, that answer must be within span of S. It can't be outside of span of S. Okay, and that's not trivial at all. We're asking a big thing here. Okay, right, so let's see why that is actually going to be true. Well, if W and W bar are elements of the span of S, that means that they are going to be linear combinations of those vectors in the set capital S. So I'll just rewrite out the set capital S here again. So the set capital S consists of these vectors v1, v2, all the way up to vn here. Okay, and if W and W bar are going to be elements of the span of S, then just by definition, because span of S only contains linear combinations of these n vectors, then W and W bar must be linear combinations of these vectors. So W will be some linear combination, so let's just write that out explicitly. It'll be C1 times V1, C2 times V2, all the way up to plus Cn Vn. Okay. Meanwhile, W bar will be some other linear combination, so it will be C1 bar V1 plus C2 bar V2, so you've got different scalars here basically, plus all the way up to Cn bar Vn. So these are two different linear combinations of these vectors V1 all the way up to Vn. Okay, right. Now what I want to do is add these two vectors together, so I can just add their linear combinations together. So if I'm considering what is W plus W bar, then really what I'm considering is what is this thing added to this thing. Okay, so let's just write this out. C1 V1 plus C2 V2 plus all the way up to Cn Vn. Okay, and I'll put brackets around that. Okay, so this great big thing corresponds to W here. And now I'm adding this, and I'll try and squeeze it in up here, to C1 bar V1 plus C2 bar V2 plus all the way along to Cn bar Vn, like so. And I'll highlight that one in pink here, and that corresponds to W bar. Now, of course, addition of vectors is beautiful. It obeys associativity and commutativity. Associativity tells us it really does not matter where you put the brackets, so you don't need to bother putting any brackets in at all, because wherever you put the brackets, the answer is going to be the same. Commutativity tells us that it doesn't matter what order you actually add them together in. Okay, so you can interchange the orders here and it doesn't matter. Okay, so that means that all of the intuitive algebraic manipulations that we used years ago when we were children hold in this. Okay, so what I can just do is move this one over so that it's next to this one. So what I'm going to do is get the terms which have the same vector in them next to each other. Okay, so remember, all of these things, C1 V1, C2 V2, Cn Vn, and all of these ones as well, these are just vectors. Yes, they're one vector scalar multiplied by some element of the field, but for now just view them as vectors. So we're just adding all of these vectors together. Okay, and because of addition being so beautiful, I can just move them all around freely. Okay, so what I'm going to do is I'm going to leave C1 V1 where it is, but I'm going to bring this one all the way up so it's next to C1 V1. So I'll have plus C1 bar V1 here. Okay, so now I've put the two ones that have a V1 here next to each other. Then what I'm going to do is I'm going to have plus C2 V2, and then you've guessed it, I want this one now to be moved up here, so I'll have plus C2 bar V2. Okay, and then it will go on, you'll have plus C3 V3 plus C3 bar V3. Okay, but I'm not going to put them all then, so I'll just put dot dot dot, and then we'll go all the way up to Cn Vn, and I'll have this now next to Cn bar Vn. Okay, so the rigorous account of why it is okay for me to do that is that addition obeys associativity and commutativity, and those two together mean that I can manipulate this around as I please, basically. Okay, right. Now what I'm going to do is I'm going to use distributivity, specifically part 1 distributivity of scalar multiplication over addition in the vector space. Okay, so what I'm going to do now is factor out. Oh, actually, no, this isn't part 1 of distributivity. This is part 2 of distributivity. Okay, this is distributivity of scalar multiplication over addition in the field. I do apologize for that. Okay, so what I'm going to do is I'm going to factor out the vectors here. Okay, so if I'm considering something of this form, C1 V1 plus C1 bar V1, okay, one of the axioms that we insist on being true concerning scalar multiplication in a vector space is that this has to be equal to this, C1 plus C1 bar times V1. Okay, and understand how different this is from this. Okay, this means firstly multiply V1 by C1, multiply V1 by C1 bar, take these two answers, okay, and this is scalar multiplication in the vector space, okay, we'll get two vectors in the vector space, and then add those two together in the vector space. Here, what this means is take C1 and C1 bar, add them together in the field. That addition sign there doesn't mean addition in the vector space. You can't add these two things together in the vector space. They're not in the vector space. They're elements of the field. So that means add them together in the field, get some new element of the field, some new scalar, and then scalar multiply that element of the field by our vector v1. Okay, but that is one of the axioms that we insist is going to be true about scalar multiplication in a vector space. Okay, and I have previously called that in previous videos part 2 of axiom number 4, that scalar multiplication must obey. It's one of the distributive laws. Okay, right, so now I'm going to do that for all of these, so I'll continue on. So for this one I'm going to do it, okay, so I'll get C2 plus C2 bar times V2, and then we'll go on all the way to this final one here, where we'll get Cn plus Cn bar times Vn, okay? Right, now why is that excellent, and why am I done here? Okay, well, because what I now have shown is that this is a linear combination. This has to be an element of the span of the set of vectors S. Okay, because all of these things, C1 plus C1 bar in the field, that's some element of the field. C2 plus C2 bar, where this addition is done in the field, is also an element of the field, and this argument continues on. Cn plus Cn bar, that's just adding two things together in the field. The field is closed under addition, so that will just be another element of the field. So I've got an element of the field times V1, plus an element of the field times V2, plus all the way up to an element of the field times Vn. That is a linear combination of the vectors in this set S, so it's an element of the span of S. Okay, so there what I have proven is that if you add together two linear combinations of vectors in this set capital S, you will get another linear combination of the vectors in that set capital S. So the span of S is indeed closed under addition. Okay, so criterion number 1 checked. Criterion number 2 then. Okay, criterion number 2 says that it must be closed under scalar multiplication. So you take any vector from the vector space. Okay, so for all, not from the vector space, from the subset, okay, and I was about to call it capital W because that's usually what a subspace is actually called. Take any vector little w from the span of S, got there in the end. Okay, so here is our subset that we're trying to prove is a subspace. Take any vector from it. In addition, take any element of the field, any scalar from the field. So for all little c is an element of the field capital F. Okay, so take any vector from the set which we're trying to prove is a subspace and take any element of the field. It must be the case that if we scalar multiply this vector by any element of the field, CW must be an element of the span of S. Okay, now I can draw a similar picture as I did over here for what that actually means in terms of the restricted composition law, and that's what I'll do now. Okay, so let me just draw out our scalar multiplication table once again. So here is our scalar multiplication table. We have all of the elements of the field given a row here. Okay, now we're not restricting the elements of the field remains exactly the same, so we're not changing this portion of the composition table. Okay, and up here, given a column, we have all the elements of the vector space capital V. This is the portion that we're restricting. We are interested in restricting the elements of the vector space down to our subset span of S. Okay, so once again, let's say that all of the elements of span of S are these columns here. They are given these columns at the start of the scalar multiplication table here. So all of these portions here, these are the portions outside of span of S. So here is our subset span of S. Okay, so now we are only interested in those columns corresponding to elements of span of S, where we're scalar multiplying elements of span of S by some element of the field. So we're only interested in these columns. I am not interested in these columns at all, because these relate to elements of the vector space that are outside of span of S. So that's what I mean by restricting down the scalar multiplication law just to the subset span of S. Okay, so what then does this condition say? This says take any element of span of S, okay, take any element of the field, okay, so any element of the field, scalar multiply them together, and the answer must be an element of the span of S. Now I hope that what you can see here is that this is really demanding that all of the entries in this restricted scalar multiplication table are back in the subset span of S, so we don't end up with elements from outside of the span of S in the vector space capital V being in this restricted scalar multiplication table. And again, that's not trivial, okay? If you just take an arbitrary subset, the likelihood is that when you restrict down the scalar multiplication table to that subset, you will end up with elements, answers in here, being in the vector space, the portion of the vector space that's outside of the span of S. Okay, so we want, when we restrict our scalar multiplication table down to the span of S, all of the answers in it to be within the span of S, not be outside of the span of S, but in the vector space. Okay, so that's what we now want to prove. Okay, so what we really want to prove then is that if we scalar multiply a linear combination of the vectors in the set capital S, that we get another linear combination of the vectors in the set capital S. Okay, so once again we'll say that W is some linear combination of the vectors in the set S, so we'll just write it out as C1 V1 plus C2 V2 all the way up to plus Cn Vn, like so. So there is what W is going to be equal to, and we can say that just because it is an element of the span of S by assumption. Okay, so it will be a linear combination of the vectors in that set capital S just by definition. Okay, right, so now what we want to do then is scalar multiply this linear combination by some scalar from the field, which I'll call C, and I hope that's not going to cause confusion. Okay, all of these are C with a subscript. This is just C without a subscript, so I hope we'll be able to tell the difference. So C times C1 times V1 plus C2 times V2 plus all the way up to Cn Vn, like so. Okay, so we want to work out what this is equal to. Now, the first thing then that we can do is apply distributivity, and now it's the other distributivity, part 1 distributivity as I called it. Okay, so one of the axioms that we insisted was going to be true for scalar multiplication is that if you had any scalar C multiplied by two vectors added to one another, so V plus V bar, that this would be equal to C times V plus C times V bar. Okay, that was one of the axioms that scalar multiplication must obey in order for our vector space to actually be a vector space. Okay, so what this is saying is that you can either add two vectors together in the vector space firstly, get some answer which is another vector in the vector space, and then scalar multiply it by C to get some final vector. Okay, or you can firstly scalar multiply V and V bar by C, and then you can add them together in the vector space. You can add those two answers together in the vector space. So effectively it says that either you can firstly add and then scalar multiply, or you can firstly scalar multiply and then add. Okay, either way round, the answer should be the same. Now, what we have never argued for before is that this can be extended. You can have an arbitrary number of vectors in here, okay, and the law holds true, but now we're going to need that to be the case. You see, what I want to say is that this is equal to C times C1 V1 plus C times C2 V2 plus all the way up to C times Cn Vn. So why does insisting that this is true mean that I can extend it for an arbitrary number of vectors in that bracket? Well, let me just argue as to why that is true. Okay, so the reason that this is going to be true is that what I can do is I can reduce this massive thing here to just being two vectors added together. And the way I can do that is I can say, okay, consider C1 V1 as being one vector, and consider the massive bit here, everything that's left, C2 V2 plus C3 V3 plus all the way up to Cn Vn. Consider all of that as being just one vector. Then I've got C times, in the brackets, two vectors added together, just like I have here. So then what I can say is that this is equal to C times C1 V1 plus C times C2 V2 plus all the way up to Cn Vn. Okay, so I've got the first bit right. Now I've got this mess though still. Okay, but now you can just do it again. Again, this is why you can eventually break this down to this. You can say, okay, let's consider C2 V2 now as being one vector, and then consider all of the rest as being one vector. So C3 V3 plus C4 V4 plus all the way up to Cn Vn. Let's consider all of that as one vector. Okay, and then we can apply distributivity again. We can say now that this, we can break it down further. So I'll firstly have the C, whoops, not that, C times C1 V1 there, okay, just from before. And then, now I've got one step closer, I'll now have the plus C times C2 V2 here, and then I'll have plus C times what's left, which is C3 V3 plus all the way up to Cn Vn, like so. Okay, right, and then you can continue on, and you can hopefully see that because I've got a finite number of things here, you will eventually finish that job, and you will split it down into this thing. So that's why, once this is true, you can then just extend it to an arbitrary number of vectors, as long as it's finite in those brackets, basically. Okay, so that's nice and simple, so we can indeed break it down into this, okay? Now what can we do? Okay, well this is screaming out to have associativity applied to it. So now we really are using all of the axioms of scalar multiplication here. So axiom number 2 that scalar multiplication in a vector space must obey is associativity. And associativity concerns just these things that we've got here. Okay, so where you firstly scalar multiplied a vector by one thing, got the answer, and then scalar multiplied that again by another vector. Well, axiom number 2 of vector spaces insists that these things must be the same as if you firstly multiply the two elements of the field, the two scalars together in the field. Okay, so associativity of scalar multiplication with field multiplication says that C times C1 times V1 is equal to C times C1 in the field times V1. Okay, and understand again how different these things are. This says scalar multiply V1 by C1. Get an answer which is in the vector space, and then scalar multiply that answer by the element of the field C. This thing here says multiply the two elements of the field, C and C1, together in the field to get another element that's in the field, and then scalar multiply that element of the field by V1. Okay, those two ways of doing this are very, very different. But axiom number 2 of a vector space says that it must be the case that those two things are true. Okay, those two things are equal to one another, rather. Okay, so that's one of the things that we just insist it has to be true in order for it to be classified as a vector space. Okay, right, but as I say, if you just made up the scalar multiplication law, the chance that this will be true is very, very low. Okay, it reflects the fact that the scalar multiplication law is absolutely beautiful. Right, okay, and we can continue this on. So we can write this as C times C2 times V2 plus all the way up to C times Cn times Vn, like so. Okay, and what have we got there? Okay, well, we've got a linear combination of the vectors v1, v2, all the way up to vn. Okay, because these things, c times c1, c times c2, all the way up to c times cn, those are just elements of the field. So this is an element of the field, this is an element of the field, all the way up to this is an element of the field, and we are just scalar multiplying those elements of the field by these vectors and then adding the things together. Okay, so this is a linear combination, so this is an element of the span of S. Okay, so that went well. We have now proven that if you scalar multiply a linear combination of the vectors in the set capital S by some element of the field, you end up with another linear combination of the vectors in S. Okay, finally then, axiom number 3. That a subset must obey in order to be a subspace. Okay, and this is the simplest one. Okay, so this is a nice one to end with. The 0 vector must be an element of that subset, and I'll just move this up. So we want the 0 vector, the additive identity of our vector space, to be an element of the span of S. Okay, now why is that going to be true? Why is the 0 vector always going to be an element of the linear combinations? Or rather, why is it always going to be a linear combination of a set of vectors? Well, whatever this set capital S is, so I'll just draw my set out again, v1, v2, all the way up to vn, one of the linear combinations is 0 times v1 plus 0 times v2 plus all the way up to 0 times vn, where these zeros here are 0 in the field. They are the scalar 0. Okay, they are the additive identity in the field. Now we know that when you multiply the additive identity by any vector, so when you go to the scalar multiplication table and look at the row corresponding to the additive identity of the field, okay, and I'll draw this on this picture for lack of space down here. So here is our scalar multiplication table. When you look at the row corresponding to the element 0 in the field, when you multiply 0 by any of the vectors in the vector space, you just get 0, 0, 0, 0, 0, 0, 0, where this is 0 in the vector space. So this 0 is not the same as these zeros. This is 0 in the field. These are all zeros in the vector space, because remember, the answers to scalar multiplication have to be vectors. Okay, so these are all the 0 vector. So the entire row corresponding to the 0 in the field is a bunch of zeros in the vector space. Okay, so what we'll end up with here is we'll end up with the 0 vector being the answer to 0 times v1, so I'll underline this in red, and then we'll be adding this again to the 0 vector, which is the answer to 0 times v2, okay, and you'll go all the way on until you add again the 0 vector here, which is 0 times vn. Okay, and when you add n lots of the 0 vector together, you end up with the 0 vector, okay, because it's the additive identity of your vector space. When you add it to itself, you get itself back again, and you can continue that as many times as you like. You're never going to get anything other than the 0 vector. Okay, so the answer to this is indeed the 0 vector. So that is why the 0 vector is always a linear combination of any set of vectors, and why it's always an element of the span of a set of vectors. And with that then, we prove that the span of S, this subset of our vector space, does indeed obey the 3 criteria that we need it to obey in order to be a subspace. So what that now tells us is that the span of S is indeed a subspace of our vector space capital V. So if you restrict the addition and scalar multiplication laws of your vector space down to this subset, which is the span of S, then that subset with those restricted composition laws on it does indeed obey the axioms of a vector space itself. It is a vector space itself. Okay, and with that we will finish this video.